Lithospheric peeling, new DOGAMI maps, and shock metamorphism in meteorites. Welcome to the GSOC Geology Hour, our monthly gathering of geology enthusiasts. Brought to you by the Geological Society of the Oregon Country with support from the Beverly Vogt PSU Scholarship Fund and the Portland State Department of Geology. I'm Alyssa Smith.
I'm Carrie Gordon.
And I'm Vince Mugica.
So this is Geology in a nutshell. This is the little segment where I'm summarizing some recent geology happenings. So our picture today is from the Alvord Desert. So I'm going to start today with a quick update on the Hawaii eruption that's been going on. Then we're going to talk about peeling lithosphere under the Sierra Nevada mountains. And then we're going to go into 3 recent DOGAMI map publications. So to start off, this is a view of the summit crater at Kilauea. And this was taken just earlier today. So 1/20/2025 at 12:50 Hawaii Standard Time. So pretty exciting thing here. And here is a time lapse of the past 24 hours to show. And I'll let it loop around because I never remember where it started. And it's pretty, it's starting to quiet down, but you can see there's still stuff happening there. So this is a map to show the location of the eruption. So this eruption started on the 23rd of December, and it's ongoing here. And the important things to point out here, unfortunately the map didn't have a scale, but the active vent is this dark purple dot here. And right next to it, there's a lighter purple dot. That is like a previous vent there. And then the red here shows the areas with the newest flows. So, and you can also see on here, there is some monitoring equipment shown. And these are things, some of these cameras you can actually tune into for a live view, which is pretty neat. So this is really recent information as of 8:25 a.m. Hawaiian Standard Time. This is the from the bulletin that they'll send out if you're subscribed to the Volcano Observatory's listserv. But the 4th eruptive phase from this eruption ended just 2 days ago, so January 18th. And they know that there's still lava near the surface because even though they don't see it like actively coming out of the ground, there's still the glow being emitted. So that shows that it's still hot and pretty close to the surface. And despite this, there hasn't been any unusual activity on the rift zones, nothing, no big earthquakes there or anything. There have been seismic tremors like at the caldera itself, but no actual earthquakes, just in the recent few days. And then they also noted that the gas emissions, specifically of sulfur dioxide or SO2, have been lower in this 4th phase than they were in the prior phases. So now thinking about hazards. So one of the big ones that happened originally was tephra fall. So tephra is just going to be, any sort of ejecta that's thrown out of the volcano. And so that's one of the roads leading, I think, up towards the summit there that was just covered in just little pyroclastic debris. And then currently, the big things are going to be volcanic gases and then also Pele's hair. So Pele's hair is a really cool product of volcanic eruptions where there's fire fountaining. So you have like hot material being thrown into the air. And then essentially these tiny droplets will get strung out by the just the motion of being thrown out and elongated. And then they kind of tangle together in this kind of golden, sort of hairy sort of stuff. This is the stuff that makes me want to get on a plane to Hawaii because I really want some of this. And reticulite's another one, but they didn't mention that. But yeah, it's a hazard technically because it can be blown by the wind, catches in small depressions. But as far as gases go, so water vapor is the biggest component of emissions, and then also carbon dioxide. But the one that's really problematic is that one that I mentioned, sulfur dioxide or SO2, because that can get into the atmosphere and under the right conditions or the wrong conditions will create smog or VOG, which is volcanic smog. So that's some gnarly stuff. And I thought it was pretty interesting that it's currently ongoing Volcano Awareness Month on the island of Hawaii. And so there was a contest that actually ended today for like volcano art and poetry, which is pretty neat. But there's a lot of stuff going on, mostly I think at Kilauea itself, to celebrate, Volcano Awareness Month and to educate. And if you're interested, that's something you can check the CVO, or not the CVO, the HVO website for more information. So that is our little Hawaii update. And now we're going to jump on a plane and go across the ocean to California. So this second bit is going to be talking about the concept of peeling lithosphere under the Sierra Nevada mountains. So there's the Sierra Nevada there. So if you're not familiar with where the Sierra Nevada mountains are at, they're in California, right about here, and this area that I just crudely drew on PowerPoint. And the Sierra Nevada is this several hundred kilometer long chain of batholiths. So granodiorite plutons that used to be underneath a volcanic arc. And so now it's just kind of the guts that are left behind. Really beautiful, and people like to hike on them. But there might be a lot that we can learn about how the Earth formed from the remnants of volcanoes, which is fascinating. So if you're not familiar with how rocky planets are formed, I know that meteorite people are way better versed on this than me, so if I slip up in here, forgive me. But essentially at the beginning of Earth, we started with this molten body that was just the composition of everything that's on Earth now. And then over time, as the Earth cooled, it segregated into a mantle and a core. And then with time, because that's not what we've got now, we had a continued process, and there's a lot of question marks in between. But essentially the setup we've got now is we've got the crust on the outside, we've got an upper mantle that has chemically differentiated from the lower mantle, which is more similar to that original mantle, and then the core below. And then so the question with that this article is going to get at is, can we see part of this process in action? You might think, okay, well, it might be hard to go back in time, but let's see what we can find out. So if we were to look down at the mantle is mostly made out of peridotite. So that's, a low silica rock made up of olivine and pyroxenes with lesser alumina phases and oxides and whatnot. But if you melt that to get like something like oceanic crust, you're going to get something akin to like a basalt or a gabbro. So the silica content increases. So you got, around 45 up to 52 weight percent silica in basalts and gabbros. But if we're thinking continental crust, that's not the type of rock that we're on. We're on something that's more buoyant, and it's going to have a higher silica content, more akin to a granite, or a granite-ish is what I wrote, because I'm a stickler about, no, granite's a very specific combination of minerals, but approximately a granite with 70 plus weight percent silica. So we have to get there from mantle composition, which can take a minute. So essentially in our current setup, what we've got is this. So we've got the continental crust on top, and that's more felsic, so higher silica, and the lower crust below, which is more mafic, right? And what happens is we can get melting in the lower crust, and those melts are going to have a higher silica content than the stuff it melts out of. And the reason for this is that you don't melt everything at once. You melt, it's called partial melting. You melt partially. And so you end up just with a higher silica content in those melts. And essentially those melts are more felsic. They've got higher silica and less dense, or rather when they solidify, they form more felsic rocks, but less dense. And then what happens is that the stuff that's left behind is, it's a concentration problem here. So it's going to be more mafic and it's going to be denser. So what you can imagine is that over time in a volcanic arc, you've got this process going on for a while, right? And this progressive differentiation essentially makes this very thick, or this very dense layer of lithosphere that's actually denser than the mantle below it. And so this residue, as it's called, is gravitationally unstable. It's not held there very well. Like I said, it's denser than what's around it. And therefore it wants to sink. So if it just continues to densify, you can have a process called delamination. And that's essentially where this layer of the lower crust will peel away. And then they call that process foundering, is when it sinks into the mantle. So now let's bring us back to the Sierra Nevada mountains. So what this study did is they used some different types of data to see if this process was something that had happened recently in the Sierra Nevada mountains. So they used seismicity data, so collected over, from 1985 to 2023, and they were looking at specifically earthquakes that were deeper than 40 kilometers. And then they used receiver function analysis. And what they did with this is to determine material boundaries and look for anisotropic structures, or essentially materials that have different properties depending on which dimension. So that's kind of important. So what they put together is this model here. And they saw this band of seismicity at 40 plus kilometers and down up to 100 kilometers. And what they found is that it was shallower under the Southern Sierra and deeper under the Central Sierra. And then they couldn't image it in the Northern Sierra. And let me finish mentioning this one. But this figure is what they interpolated from those data. So what they saw is they could see is this kind of ongoing shear process, because they have this anisotropic structure that is essentially stretched, and it's peeling towards to the west essentially. So this is what they interpreted as being that lower lithosphere level. And the significance here, is that this seismicity at 40 kilometers or greater is really unusual outside of a subduction zone. It's not something that we would expect, at part of the continent that is, essentially on a transform boundary now. But it agrees with previous models that said that they believed that there had been this lithospheric removal in the Southern Sierra at about 4 million years ago, and that they believe this process is continuing then in the Central Sierra Nevada mountains. So really cool study. And now we're going to move on to my last bit here to talk about some recent DOGAMI publications. So there's a geologic map of the Mill Creek area, landslide inventory and risk reduction in Grant County, and then channel migration zone maps for the Zigzag River. So this first one here is the geologic map of the Mill Creek area, and that's over by Hood River. And this is a 210-page report and also includes 3 separate geological maps, and then also includes GIS data. So if you like to play with GIS data, this looks like a really cool one. And this here shows the area where these maps were conducted. So I put little cities there to show Hood River and the Dalles, made them look much more metropolitan than either of those places maybe in reality. But it's the Ketchum Reservoir, the Brown Creek, and the 5 Mile Butte quadrangles. And so the orange here are quadrangles and areas that have been recently mapped by DOGAMI. The blue are areas where there are USGS maps in progress. And then the kind of mauve color there are future maps for either USGS or DOGAMI. And then again, that red box shows this study. So this study is part of a multi-year study of the Middle Columbia Basin. And some of the reasons for that are some of the things they're looking at rather are going to be the geological history of the Northern Oregon Cascades. So this is, slightly different than the area I work at in Central Oregon. Little different tectonics going on there. They're looking at the structure of the Yakima Fold Belt. So this is kind of where these two kind of regions come together. And then also looking at the stratigraphy of the area, kind of under the idea of looking for water resources. And then there's always the question of aggregate and mineral resources. We always need to build things, and mineral resources are only becoming more and more important. And lastly, geologic hazards, so keeping people safe. So this is one of the inserts from the map. I couldn't put all of them in a slide, so I just picked the one I thought was the prettiest. This is the cross-sectional view for the Brown Creek quadrangle. So really neat structural detail there. And the sort of data that were included with this publication were, so they sampled, or they went to over 950 different field locations from 2011 to 2018, and then collected over 350 rock samples throughout the whole area. And from that, they got 249 new XRF analyses, and they combined those with, I think, just about 50 pre-existing ones. There were some collected out there, but brand new bulk rock analyses. And then they used 6 compiled potassium argon ages and 59 petrographic thin sections. And there were also 93 new magnetization measurements. And the one I think is so wild is over almost 1,200 orientation measurements throughout this area. So a ton of work went into this. Really beautiful maps. The second one is looking at the landslide inventory and risk reduction in Grant County. And so this one is a shorter report, 36 pages, and includes 4 separate maps and also has GIS data. And the bonus with this one that is really neat for just anybody who wants to like take a look at a map in a very accessible way is that there's actually a GIS like story map available. And that's something you can just open in your web browser and click around and look at the data for yourself, which I think is neat. So I'll show you what that looks like in a few minutes. So if you're not familiar with Grant County, there it is. And so the study regions were just a few of these locations throughout Grant County. So not the entire thing, but a few key areas. And so this is what one of these maps would look like. So the thing is with landslides is they're one of the most widespread and the most damaging natural hazards that occur in Oregon. And so looking into how these impact humans is kind of important. So what's included on these maps, first off, we've got the scale there. So you can see actually the size of things we're looking at. And then a legend to show you everything that's there. And here is where they tell you what types of landslides. These are kind of like the sort of activity that will happen, the features that will happen. And then also in the letters that were on here, I didn't include this table here because it would get just too busy. But they also have classification of the movement. So like RF on here would be like a rock fall. So there's information not only about where they are, but what and how they would occur. And so the significance with this is that, they increased the number of mapped landslides wildly. So there had been 81 previously recorded, and there are over 1,500 included in this report. So just a general improvement on the understanding in this area. And that also includes like different varieties of landslides. So deep-seated landslides, debris flows, rock falls, shallow landslides. And there's a big focus on this in risk reduction. So understanding this is really important. And they're trying to target public awareness with this. And this is important for people who in the area who are planning, or if there's regulations that need to be in place. And then also for emergency response in case of some sort of event. And this is a look at what the interactive story map looks like. So I haven't quite figured out how to actually put something like this in PowerPoint, but I got a screenshot. So what you can do with this is you can look at it from further out, and then you can actually zoom into the different areas and click on the little polygons themselves, so you can actually interact with the data in a more, like personal sense, which I always think is great. So the last report for today is the some recent work that was done for the Zigzag River up by Mount Hood, specifically looking at channel migration zone maps for the Zigzag River. So this is a 43-page report that also includes maps. So these ones are actually built into the report instead of being separate. And this also comes with GIS data. So if you're not familiar with where the Zigzag River is, it's a river off of Mount Hood. So it goes from the south slopes of Mount Hood and then down. And so this is the yellow area is the part of the Zigzag River they were looking at. but this is an important river because it's one of the major tributaries to the Sandy River. So the purpose of this whole study was to look at where these streams are, and see where they might move laterally based on how they've behaved in the past, but also the conditions at the present. And one of the things that I thought was really striking about this is that the sorts of assessments that are done for like FEMA flood insurance maps only include the river as it is, and they don't account for channel migration. So this sort of model could be really, really helpful if you're trying to figure out where to put your house. So this is one of these maps, and it's got a lot of different colors on it. So I wanted to call these out separately to be just a little bit more exciting than just showing a still picture. So the blue here is our active channel, and then the teal color is the historical migration area. So areas that they've seen in historic times where the river has ended up. There's also an important thing here over by Mount Hood is flagging areas where the river is going through pyroclastic deposits. So there's the solid color, which has been just like that's going through pyroclastic deposits. And I believe the dashed is areas where it's gone through kind of like more recent deposits, or I might have those backwards. Then we've got the 3 shades of green here are erosion hazard areas. And the dark green is the area where it's like the highest probability of it eroding, and the medium green is the medium danger, and then the light green is the lowest probability. So that's more in the case of like a 100-year flood, whereas the other two are like a 30-year flood. So more pressing generally. Then we've got the avulsion hazard area, and that one is the place where oh no, I lost my notes, but essentially those are the highest danger areas as far as erosion is going to go. And then the whole thing is wrapped up in this magenta, which is the channel migration zone. So they did this for the entire river, or at least the portion that they were looking at. So let's take a look at that. So this is, like I said, they didn't do the whole river. They did the lower portion. So they did the lower 7.8 miles. And so you can look at these different zones for the entire lower 7.8 miles. So I sutured these together and it worked pretty well. So you can see the whole length of where this work was done. So it's a really impressive report, and I think it's really neat. And I know that these reports haven't been done for many areas in Oregon, but hopefully that's something that they can progress towards doing more, especially as our population grows in Oregon and people need to live places.
So we've got one question in here. What is XRF?
Oh, XRF. So that's a type of chemical analyses that's done through X-ray fluorescence. And so essentially what you do is you have, you prep your material in a certain way, and then you shoot the material with X-rays, and the material will reflect or refract X-ray. Yeah. And essentially the amount of energy that's put off by the photons emitted from that particle will tell you the composition of what you're looking at. It's pretty cool. It gets us a number of elements. It doesn't analyze all elements, but a good chunk of them. So
John Springer wants to know, what would have happened 4 million years ago to cause movement under the Sierras? I think that's referring to the delamination.
yeah, I should have checked into that, but I'm not 100% sure. I'm not sure if I know that it was based off another study I glanced at previously. I'm not sure. I'll have to look into that. Yeah, because that's an area that, I mean, the volcanic chain, so the batholith, the Sierra Nevada batholith is Jurassic in age. So it was a while ago. And a lot of you just have to remove all that stuff. So I'm not sure what it's tied to.
Any idea of why the delamination occurred first under the southern Sierra? It's kind of interesting that it seems to be slowly moving north.
My biggest guess is that that's kind of the way the propagation of like the San Andreas Fault has gone. Has and everything starting from like the Salton Sea upwards has started from Southern California up, and so I think that's just kind of the general trend, and that's what it's kind of expected to continue with continued movement, assuming it doesn't. I know there's talk also about the Sierra or not about the San Andreas eventually the movement being manifested on a different fault, like, but the general motion has been kind of that direction. That's a great question.
Oh, that's wonderful. And I, for one, was really happy to see both the landslide mapping for Grant County as well as looking at the Zigzag River, because both of those are dealing with people and risks, and where the risks happen or where people, it's geologic activity is going to happen, but where
Yes.
you have the geologic hazard is when you have that cross section of people with landslides or rivers moving. And I think that is wonderful to see that information coming out to the public.
Yes. And there were even, I think since I picked these articles, I think two more that came out that were put up. So there's even more that you can look at.
Thank you, Alyssa. And Vince, it's yours.
Thank you, Carrie. Thank you, everybody. Thank you, Alyssa. It's going to be very difficult to follow that. I'm really happy to be joining you all today, and I'm going to be discussing my research at Cascadia Meteorite Lab on shock veins in meteorites. So I'm a member of the Cascadia Meteorite Laboratory, and you can see a few of the grad students, undergrads, and our advisors here. The work that we do at Cascadia Meteorite Laboratory at Portland State University really focuses on the physical, chemical, and material properties of meteorites. So we specialize in optical and electron microscopy and electron backscatter diffraction methods. But we also do meteorite classification as well. And so I kind of want to start off my talk by really explaining what motivates me, why I chose to do this work for a master's thesis. And it really comes down to this opinion that I have that you all can agree, debate with me after or at some point. But I really feel passionate about this. And I believe that hypervelocity impacts are the most fundamental process in all of geology. And it is for this reason, it is for this view that I study meteorites. And so what are meteorites and why do I study them? Well, meteorites, you can see one here. NWA 869 is its name in Northwest Africa, because that's where we find a lot of meteorites. And you can't really understand what meteorites are until you understand the impact process. And so meteorites are the fragmented rock that is ejected from impact events in the solar system. And so their impact process is really divided up into different stages. And so the first stage is this contact and compression stage. And you can see this little cloud here depicting ejecta. And that's actually where meteorites come from. Meteorites are the ejecta during the stage from these impact events. Other stages include the excavation stage. This blue line is supposed to represent a traversing shock wave, and it's actually that interaction that is really the focus of a lot of my work that we'll get into in a bit. And then the final stage in the impact process is the modification stage. Here's another figure here that sort of illustrates what's happening. One thing I want to explain here is we have these values here and these contours, and these values here, 50, 20, 10, 5, are pressure in GPa. And so when you have an asteroid impacting, let's say, another asteroid in space, let's say billions of years ago, it'll be the case that it'll make contact with the target material, and there'll be a sort of gradation of pressures and temperatures that the target material experiences as a result of the projectile. And it's sort of this impact process that creates something called shock metamorphism. And most of us here are, terrestrial geologists. We just think of traditional metamorphism. And so I'll be talking to you today about shock metamorphism here. Here's a sort of another figure that sort of illustrates the impact process and kind of what's happening between the the target material and the projectile during an impact event. Again, you can see this gradient of pressure. So we have very high pressures and rocks that melt very close to the impactor, and then as we move away from the impact site, we sort of get less pressures that the rock experience. And of course, you can see this line here that represents this propagating shock wave that is created as a result of these hypervelocity impact events. And so you may be asking, okay, well, how do we get meteorites? Well, when these meteorites blast off from these impact events, they traverse through space. And what you're looking at here is a picture of the Sahara, so North Africa, and it's a desert. And meteorites are found in hot deserts and cold deserts. A lot of them are found in North Africa, and that's where we can get a lot of meteorites from. And it turns out that there's a lot of very skilled meteorite hunters in North Africa who are, with very great accuracy, they're able to identify these rocks that stick out in the sand, and they could actually, with pretty good accuracy, tell us what kind of meteorite it is. It's very impressive. And so obviously North Africa has very large surface area, and so you could imagine that we get a lot of meteorites from that part of the world. Of course, our Earth is covered in 70% ocean, and so most meteorites, unfortunately, end up in the ocean. So, the fishes are happy. And before I kind of get into the details of my research, I kind of want to talk about the major divisions of meteorites. So there's really two major divisions, and we could think about them in some different ways. So the first division, there's like really two types of meteorites. There's achondrites and then there's chondrites. Achondrites are meteorites that crystallized from magma on other planets, like the Moon, Mars, or some asteroids. Chondrites are meteorites that accreted and condensed from material in the solar protoplanetary disk. So the beginning of our solar system, it was a solar protoplanetary disk that formed around a stellar object. And as cooling commenced, we had a condensation and accretion of material. And that's where chondrites come from. There we go. Another way to think about this sort of big segregation of achondrites versus chondrites is we can think about the parent bodies within which they come from. So achondrites, they come from differentiated parent bodies, and Alyssa talked a little bit about this in her presentation. But differentiated bodies have segregated interior divisions, right? So Earth has a crust, we have a ferromagnesian silicate mantle, we have an iron nickel core, and that is roughly the case with other differentiated bodies as well. Chondrites, on the other hand, come from undifferentiated parent bodies. And so you can see here that in the solar protoplanetary disk, we had an accretion of ices, silicate condensates, iron nickel metal, all kinds of junk that is just really random. And that is the sort of good depiction of where chondrites came from and the nature of their parent bodies. And so again, global melting had to have occurred in order to differentiate some differentiated parent bodies like Mars and the Moon. And so that's important to keep in mind. So again, the focus of my work is on shock veins in ordinary chondrites, specifically L chondrites. And it turns out that these L chondrites are from a parent body called the L chondrite parent body. Very creative. Geologists are always very creative with names. And we can call it the LCPD for short. And it turns out there is this impact event that happened 470 million years ago, the largest impact event to have occurred in our solar system in the past 3 billion years was this LCPD impact event. And it was so large that actually they find little chondrite minerals in stratigraphy, in stratigraphic columns, and they found them in the Thorsberg quarry, in marine limestone. And this is like during the Middle Ordovician. You can see in the background here, I have a picture of the Thorsberg quarry. And so this impact event was so large, and it's actually debated on where exactly it happened. Did it happen in the asteroid belt, or was there an impact event that happened basically near Earth? But we won't get into that. But there was a large impact event, and that's where chondrites come from. And so again, I'm going to be talking about shock metamorphism of meteorites. And that refers to the chemical crystallographic and textural changes in meteorites due to extreme shock induced by hypervelocity impacts. When you think of hypervelocity impacts, you want to think of tens of kilometers per second. So very, very fast, way faster than me when I wake up and get ready. So shock metamorphism affects all meteorites. There's this term called the Hugonnian elastic limit. That is the maximum stress that a geomaterial can experience without being permanently deformed. Above this threshold, geomaterials start to display shock deformational effects that we're going to look at now. So when you take an optical microscope and you look, at a thin section and you're looking for shock deformational effects in a meteorite, this is what you're going to see. This is a XPL, cross-polarized light of olivine. And you could see these lineations here, these lines. These are planar fractures. And this results from crystallographic distortion from shock. And so another sort of characteristic we see is changes in something called extinction. And so, some of you may have looked through a microscope and at a thin section of a rock, and you'll notice that sometimes, as you rotate the stage, the minerals will go extinct. And one of the things that shock does is it distorts the crystal structure and it creates this mosaicism. So these are some of the shock deformational effects that we can observe in rocks, meteorites that have been heavily shocked. And one of the things that workers have tried to do over the past several decades is they try to create this really large, shock stage classification where we can try to categorize the intensity and severity of shock in rocks with a table that you see before you. It's not perfect. There's some inaccuracies, but we do ascribe or assign a shock stage to particular rocks, and some of them are more shocked than others. So here's an example. So this is a thin section of Johnson City, L6. It's just the type of the meteorite that it is. And you can probably guess from looking at the picture, you can see S5, and you probably intuitively can figure out that S5 is more heavily shocked than S4, and that's exactly how it works. And one of the things you're going to see here is a shock vein, which is really what we're going to be talking about. And you'll notice that shock actually gets it's more intense close to the vein, and as we move away from the vein, shock gets less intense, and that's actually just indicative of the heterogeneous response that meteorites undergo. And so really what we're talking about when we talk about assigning a shock stage to a meteorite is we're talking about something called shock thermobarometry. So we're trying to determine the characteristics and the conditions of the shock event that created that meteorite, and that's called shock thermobarometry. So let's get into shock melt veins. So shock melt veins are one type of shock deformational effect. I mentioned a few others before, and you can see this beautiful thin section here. This is XPL. This is one of my thesis samples, Buck Mountains 005. And you can see this beautifully zoned shock melt vein here. And so this was literal melt that was injected into the host rock during that hypervelocity impact event. And we can see here some more shock melts. You can see that they can take some pretty amorphous looking morphologies. And you'll notice that scientists like to classify the shock stages considered more intense in the melt. And then away from the shock melt vein, we have characteristics that are indicative of a less intense shock. So this is a 10M. This is another thesis sample of mine, although I didn't take that picture. So here we have a figure of a cartoon I like of a shock melt vein and a host rock, as we call it. And what I'm trying to show here is that basically shock melt veins have very different mineralogy compared to their host rocks. So we have the colors associated with different types of high pressure minerals that actually form in these shock melt veins. And so they can obviously take very different morphologies. These are two other potential thesis candidates of mine. And you can see that these shock melt veins can be really nasty and amorphous, and they can be really interesting and forked. So here's another thesis sample of 10ham. You can see in this case, the shock melt vein is really, really thin. And what you're looking at here is a dark blue mineral. This is in plain polarized light. This is ringwoodite. So ringwoodite is a high pressure polymorph of olivine. Some more ringwoodite here. You can see all this gorgeous dark blue, this dark blue ringwoodite here that formed, and they only form inside the vein. In this case, this is an emerald green mineral called wadsleyite. This is another high pressure polymorph of olivine. And so how do these shock melt veins form? Well, in a nutshell, they form by frictional heating along shear zones. So I don't know if you can see my screen, but essentially during compression, dynamic compression, the rock has void spaces. The rocks are naturally porous. In the case of chondrites, they're naturally porous. And so when this shock compression occurs, you get this sort of frictional slipping that occurs. And when that happens, it creates this frictional heating, and that's what causes melting. And these shock melt veins, they melt, obviously, so they heat up, but then they rapidly cool by heat conduction to the surrounding host rock. That's really how they form. Here's another sort of cartoon, I think, that really illustrates the point. So you have this really large collision that happens between two asteroids, and then that shock wave traverses through the rock, and then you get these little dark shock melt veins that form. And sometimes a host rock will get enshrined in that shock melt vein, and then you'll have, it's a melt. And so you'll have minerals that crystallize from that melt. So again, here's a false color, what's called a large area map of one of my sample meteorites called Tenham. And you'll notice at the top here, there's a color key, and that shows you the kind of minerals that you're seeing. And so this is a chondrite. I'm sorry, this is a chondrite, and chondrites are ultramafic rocks. So there's a lot of olivine, there's a lot of enstatite. And the biggest point that I wanted to give you here is that you'll look at the host rock, and it has a very different mineralogy than the shock melt vein. The shock melt vein has very high pressure minerals in it. It has ringwoodite, it has majorite pyrope garnet, and those are high pressure minerals. And just, I think that this picture really encapsulates how different these shock melt veins are mineralogically from their host rock. It's beautiful. So here are two other, so the top false color image here. And this is color coordinated by elements. So you're seeing a false color EDS chemical map. And this is of a shock vein tenem, one you just saw, but you're getting kind of a different view of it. And it's showing you that there's a lot of host rock that gets enshrined in these shock melt veins. And you can see this really bright green colors. These are sulfides that get in there. They form sulfide blebs, as we call them. And then here's the Buck Mountains shock melt vein that has this weird zone structure. So these are very different morphologically, and that's actually significant for their form. So these high pressure minerals exist in these shock melt veins, but how do they form? Well, they actually can form proximal to shock melt veins as well. And what happens is basically you have high pressure minerals. They can crystallize out of melt, and they can form from solid state formational mechanisms, which I think I have in a slide here. But these high pressure minerals, I mentioned ringwoodite, for example. In this case, you can see emerald green wadsleyite in this shock vein. They can actually back transform to their low pressure olivine polymorph, depending on the relationship between pressure and temperature as it diffuses through the meteorite during shock. And so again, there are several types of high pressure minerals that we have in these veins. We have a ringwoodite wadsleyite, which I mentioned. And here's another false color EDS elemental map. And we can see majorite pyrope, which forms the matrix in Tenham. And then we have this polycrystalline wadsleyite class. And then we have this feldspathic sodic glass here. And so, like, again, these minerals are the micron scale, nano to micron scale, so very small. Another common high pressure mineral that we get proximal to these shock melt veins is mescalinite. So this is high pressure distorted plagioclase. And so when plagioclase is shocked, it turns into this distorted glass. It actually does have crystallographic order in the short range, but in long range, it doesn't. And so again, another high pressure mineral is Meteorite pyrope. And this is a solid solution. And this is just another false color map here. And the red and the dark is Meteorite pyrope. And we have this olivine polycrystalline clast. So they can take a lot of different shapes. Another image here, another SEM scanning electron microscope image of Majorite, which is garnet. These little euhedral, subhedral looking guys here are all little garnets. And note the scale at the bottom right there. Another interesting high pressure mineral that's gotten a lot of attention lately is this albitic jadeite. And so it has this really weird polycrystalline morphology. And this polycrystalline morphology actually occurs from solid state diffusion. And so I mentioned that these high pressure minerals form via crystallization or solid state formational mechanisms. And that polycrystalline sort of morphology is a result of diffusion, just ionic diffusion, which is subsolidus. And I think this is the last high pressure mineral, but this is really exciting. So I haven't seen bridgmanite because it's so small in my Tenham meteorite, but bridgmanite is the most abundant mineral on Earth, and it's been found in a shock melt vein in a meteorite. And that's kind of the catch with these high pressure minerals is they actually exist in the interior of the Earth and by extension other planets. So bridgmanite was found in Tenham using different methods, but it dominates our lower mantle. It's the most common mineral in Earth volumetrically, I think. And so I mentioned wadsleyite and ringwoodite. Those also occupy the transition zone. So what you're looking at here is a figure with depth on the y-axis here, and then just showing us the types of minerals that we see on the right here. But this is basically showing us the different interior divisions of our planet and the mineralogy. And so, yes, these high pressure minerals that form in these shock melt veins and meteorites dominate the interior of our planet. And that has to do with the extreme pressure temperature conditions of not only the interior of our planet, but the hypervelocity impact events that create shock melt veins. So why do we care? Why do I study high pressure minerals? Why is it important? Well, the first thing to understand about shock melt veins, and Alyssa also alluded to this in her presentation, is that the Earth formed from a bulk chondritic composition. So a bunch of chondrite, accretion occurred. That's how the planet's formed, by accretion, impacts, hence, why impacts are so important. And shock melt veins are actually argued to be great proxies for Earth during its magma ocean phase. And so that's sort of one big central reason why I'm fascinated by studying shock melt veins. Another reason why we study them is because high pressure minerals can help constrain the shock conditions. So when a hypervelocity impact event occurs, we want to understand, okay, well, how intense were the pressures, right? Was it a small impact or a significant impact? What were the temperature ranges? Was it really hot? Was it really cold? And then finally, what was the nature of the shock wave? So when that impact occurs, there's basically a spherical shock wave. According to shockwave physics, it's about spherical, and it propagates through the rock, the impactor, and the target material. What was the nature of that shock wave? What was the pulse duration time? High pressure minerals can help us put constraints on that. So again, high pressure minerals can form via crystallization from shock melts, something that a lot of igneous petrologists, that's very intuitive, right? Minerals crystallize from melt. We can all understand that. And then we have solid state formational mechanisms, which are really weird, and you normally need very, very expensive and sensitive equipment to make those arguments. But solid state formational mechanisms are basically ionic diffusion in the sort of subsolidus temperatures, but that can also happen as well. So how do high pressure minerals help us reconstruct impact events that created meteorites? Well, it kind of all falls under this sort of concept. I want to introduce this concept called the mineral stability field. And so basically, you have a mineral that has a certain pressure temperature range that it's stable. And if that pressure and temperature, starts to fall or change, that mineral is no longer stable, right? So if I'm here in mineral B, I'm at very high temperatures and high pressures. And if I drop pressure So I go negative along the x-axis and I drop temperature. I go negative along the y-axis. Mineral B is no longer stable, and now mineral A is stable. So it's one of the reasons why those high pressure minerals I mentioned are prolific in the interiors of planets and not so much in the surface. I think Bowen's reaction series is kind of a good sort of analogy to what I'm saying. The idea here is that with a change in temperature conditions, we have a change in the types of minerals that we would expect to either crystallize or um, um, melt. So here's a phase diagram, and just to kind of illustrate the point here, this is the mineral formula for olivine. And so basically what this is showing us is that, regular olivine, regular Joe olivine is stable under about 15 GPa. And then we have wadsleyite, which the sign here is beta olivine. That means wadsleyite. Wadsleyite is a bit more stronger, a bit more robust, and he's more stable, above 15 GPa. And then, ringwoodite is super stable. So he likes to exist, 20 to 25 GPa. And so the idea here is that different minerals have different stability ranges in terms of pressure and temperature. And so this is a phase diagram, and that helps us make inferences about the conditions that these meteorites must have experienced. So it all comes down to this. The existence of high pressure minerals in shock melt veins means that the meteorite must have experienced PT conditions, pressure temperature conditions, that stabilize those minerals. So if those minerals were not in the shock melt vein, then the meteorite must have either, it must have experienced those conditions transiently or not at all. Put another way. So I may not have time to totally go through this, but one thing that sort of helps us understand the behavior of meteorites is the concept of the Hugoniot. The Hugoniot is like this mathematical equation that tells us about the nature of shock waves. And there's a lot of, I'm not a mathematician, but these equations are very, very important because they tell us, why do we have two different sort of phases in a meteorite? We have like the shock melt vein, and then we have this bulk rock that didn't melt. That's weird. And so the Hugoniot equations actually tell us sort of how a rock is going to behave under dynamic compression. And the Hugoniot equations are actually called equations of state. And I don't know if you guys recall this, but you actually are aware of an equation of state. I'm running out of time, so I have to speed through this, but you're actually aware of an equation of state. I don't know if you remember PV equals nRT in general chemistry 1. But PV nRT is an equation of state. And equations of state are very important because they allow us to put constraints on a system if we know certain extensive or state variables of that system. And so the Hugoniot basically allows us to know why did the meteorite, why did the host not melt, and then why did the shock melt vein melt? And so here, I want to show you guys this. Where is it at here? Murchison. Okay, so Murchison is a meteorite, this blue line here. If you look at the x-axis, we have temperature and we have pressure on the y-axis. So when these lines are called Hugoniots. And so what's happening here is that as this line moves up, as we increase temperature and pressure, which will happen during an impact event, this line is telling you what Murchison is going to be doing. So if I have a meteorite like Murchison and I shock it to, I don't know, let's say 40 GPa, it's going to melt. It's going to melt because, let's say I have it at, I don't know, 2000 degrees Kelvin. It's going to melt. And so we can actually know how all of these rock types are going to behave with these Hugoniot equations. And so that's very useful for my work. And I am running out of time. So I think the final thing that I'll say is the sort of preliminary results that I've acquired. The work that GSOC has supported and that I've done and that I will continue to do until my defense very soon has really involved these two meteorites, and it'll probably involve one more or two more. And the research questions of my master's thesis really there's actually quite a few. I'm supposed to reconstruct the pressure, temperature, time conditions of the meteorite impact events. I'm supposed to evaluate the nature of shock deformation in relation to shock melt veins. And I'm supposed to utilize electron backscatter diffraction methods to evaluate the post-impact conditions of these meteorites. Another thing I want to do is when these shock events happen, you may have the question of, does that chemically alter the rock? In fact, it does. And I mentioned the Hugoniot because one of the special techniques that we use electron backscatter diffraction techniques. We've actually been able to independently verify that when these impact events happen and heat traverses through a meteorite, it actually is giving us a temperature, a syn deformational temperature for a liquidus mineral, olivine, that is pretty compatible with a independently calculated Hugoniot of an L-chondrite. And so we have this case of, two different labs that are converging on the same data point or result, which I think is very exciting. Another sort of preliminary result we have is that my meteorite Tenham, it must have experienced a shock pressure up to 17 to 25 GPa, which is very intense. And that's significant because Tenham is an L-chondrite, like I mentioned earlier. And so what I've just done is I've put a constraint on where this rock must have been in that impact event. You'll see a 20 GPa here. So I can actually place where my rocks were at that impact event. If these rocks were closer, they would have melted completely. And the fact that they haven't means that I could probably place it right around here. So it was pretty close to the impact point, but not close enough to completely get destroyed and melt. And I think that's exciting that I can do that with this high pressure mineral data. And then another thing I want to explain is that these shock melt veins, they actually have a concentration of deformation. So when these impact events happen, that shock wave traverses through the rock and it deforms the minerals. And what you're looking at here is what's called a large area map of Tenham, one of my meteorites. And at the bottom left here, you'll see this color coordinated key, and it's 0.1 degrees to 15 degrees. And that's just a measure of deformation. And you probably get the idea. Blue means low deformation, red means high deformation. And one of the things you'll notice here is that there's actually pretty significant deformation close to the shock melt vein. And so this kind of goes to one of the questions of the research that I'm doing, which is trying to put constraints on the nature of deformation in these meteorites in relation to shock melt veins. And so this also independently supports a frictional heating model for the formation of shock melt veins, because you'll actually notice there's kind of a right lateral thing going on here. You'll notice there's a concentration of deformation here and here. Oh, there we go. And then lastly, we do have preliminary evidence that there are chemical alterations that occur in these shock melt veins, and that chemical alteration is distinct from the host rock, particularly sodium. Sodium is a large ion, a very large element, makes it very mobile during these intense shock events. And so we have preliminary evidence for that. Unfortunately, if you want to get more information and more details, I do have a lot more data that I did not share, but I'd love to talk about it with you in my thesis defense. And thank you very much for listening.
Oh, Vince, this was absolutely fascinating. Is there any sort of understanding of how many meteorites may hit the Earth in a year? I'm assuming it's like thousands.
Yeah, yes. So the short answer is yes. I have seen multiple papers where workers have tried to calculate the flux of extraterrestrial material, and as you know, you guys all know, most of it ends up in the ocean. I don't have the exact numbers for you, but yes, there's a lot of literature on calculating the flux of meteorite material. We can actually, I could give you a number, but I don't have the number in my head, but there is a number though.
That's okay. And a corollary to that is, what about the size of the meteorites? What percent are greater than maybe 5 pounds, or what are the other sizes? What can we expect to see?
Yeah, meteorites can take up a lot of different sizes. Some of them can be tons, Some of them can be tens of tons. Maybe Daniel can chime in. Some of them can be very small. Um, so they can take I mean, some of them can be the size of a car. They can definitely take up a lot of different ranges of sizes. You have to keep in mind that when a meteorite traverses through the atmosphere, you can think of the atmosphere as kind of a liquid, and so the meteorite has to traverse through that, and then it undergoes ablation, and so some of the material melts and vaporizes, and so that affects the size of the meteorites.